So are we going to record? Oh.
Yeah.
Yeah, this is yeah, one exactly. Okay.
Let's see. Okay, good morning, everyone. It's a real pleasure today to have Professor Hao Yu speak to us. And Hao is an associate professor in the Department of Modern Mechanics at the University of Science and Technology of China. That's abbreviated as USTC. He received his PhD in solid mechanics from that university in 2021. And his research, it focuses on computational mechanics, numerical methods, and their applications in deep, unconventional energy development. And his research outcomes, and this is always a nice thing, have been implemented in major state-owned enterprises and leading energy companies. And he's led multiple national research projects and industry-funded R&D projects. He's published over 50 scientific papers as the first or corresponding authors in a number of leading journals, and listed in his bio. And his research has been recognized by the Anhui Province Science and Technology Progress Award, the Chinese Academy of Sciences President Award, and he's included among the world's top 2% scientists. So it's a real pleasure to turn things over to Hao. And Hao, please go ahead and share your screen.
Okay. Thank you, John, for your introduction. Okay, let's begin the presentation. Okay. Good morning or good afternoon, everyone. Thank you very much for the invitation and for the opportunity to share some of our recent work on hydraulic fracturing in layered rock formations. Today, I would like to discuss a question that appears quite simple, but becomes surprisingly subtle once geological layering is introduced. How should we describe the hydraulic fracture propagation when fracture repeatedly encounters material interface? The main message of this talk is that interface introduce a new spatial scale and therefore break the classical safe linear structure of hydraulic fracture propagation in KGD model. However, the resulting transient behavior is not arbitrary. We find that it can be organized by a unified temporal-spatial scanning node. I will first discuss the physical motivation and then introduce the governing framework, examine the response to a single interface, and finally show how the single interface picture leads naturally to a unified description of multilayer propagation. We all know fluid ground fracturing is a very broad class of coupled solid fluid process. It means pressurized fluid opens a discontinuity and drives its propagation through a solid medium. As the examples on this slide illustrate, this mechanism appears across a remarkable range of scales. In natural systems, it involved a magma transport, volcanic fracturing, and fluid-induced fault activation. In engineering, the same basic physics appears in receiver stimulation, geothermal development, mining, and related subsurface technologies. In engineering hydraulic fracturing, high-pressure fluid is injected through a well, and the fluid pressure opens the rock, and the resulting fracture creates conductive pathways in a non-permeability formation. The engineering objective is therefore not simply to initiate a fracture. We need to predict its geometry, the length, the height, the direction, and the connectivity. One important practical issue is the vertical growth. The fracture may extend a long distance laterally, but remain strongly confined in height. That behavior is closely related to vertical heterogeneity of stress and mechanical properties. Let me briefly recall the classical homogeneous picture. In plane strain, the fracture opening and pressure are linked through the elastic balance equation. The fluid flow is governed by lubrication theory. So a pressure gradient drives viscous flow inside the fracture, and the fracture tip, the linear elastic fracture mechanics, gives the familiar square root opening asymptote controlled by fracture toughness. The computation between the energetic cost of creating new fracture surface and viscous dissipation in the fluid can be summarized by a dimensionless toughness, which I denote here by calligraphic K. This parameter organizes the classical propagation regimes, and the large dimensionless toughness fracture resistance dominates, and the small dimensionless toughness viscous dissipation dominates. This asymptotic structure is extremely powerful in homogeneous media because it needs to save the linear solution and clear scaling laws. This question is what survives once a fixed geological interface is inserted into the problem. For the plane strain model, the two limit regime can be written in safe familiar form in KGD model. On the left is the toughness-dominated solution, and on the right is the viscosity-dominated solution with a different set of scalings. I do not want to go through every coefficient on this slide. The key point is structural. In a homogeneous material, the scanned opening and the pressure profiles can remain invariant while dimension fracture grows. This means that one evolving length scale is sufficient to describe the geometry of the hydraulic fracture. Once an interface introduces an additional fixed distance, that simplicity is lost. The fracture can no longer be described only by its current length. Its position relative to the interface also matters. Real shear reservoirs are strongly heterogeneous and layered. The example shown here is from the Gulong shear in China. The profiles demonstrate substantial variation in elastic modulus and in-situ stress with depth. The bending fracture density also changes significantly. The important point is not a particular numerical value, it is the coexistence of the multiple heterogeneity scales. A hydraulic fracture may encounter relatively thin mechanical layers, thinner laminar bending planes, and changes in stress over a comparatively short propagation distance. Layer-to-layer variations can act as effective barriers to vertical fracture propagation. The schematic and numerical width profiles illustrate the basic mechanism. When fracture encounters a layer with a less favorable stress state, the opening becomes confined and the vertical growth is reduced. This is consistent with the field scan observation shown by the microseismic cloud. The lateral extension can reach roughly 200 or 300 meters, while the vertical extent can remain below 0.1 of meters. So the layered structure is not a small correction to a homogeneous solution. it can control the macro scope of geometry. We need more than a static statement such a high stress is a barrier. We need to understand how the fracture dynamically adjusts after it crosses each interface. When fracture tip crosses an interface, the local tip conditions changes immediately because the material property and the corrective have changed. However, the entire fracture cannot adjust instantaneously. The opening and pressure field must evolve through fluid redistribution. This creates a separation between a fast local response and a slow global adjustment. As a result, the interface can temporarily generate a hybrid propagation region. Even if the fracture is toughness-dominated before and after crossing, viscosity dissipation can become important during the transition because fluid must redistributed to accommodate the new opening profile. The stress of the disturbance therefore depends on not only on the property contrast, but also on the distance and time elapsed since the interface was crossed. A natural response to fine layering is to introduce an effective fracture toughness. There are several ways to do this. One approach is to define a fixed equivalent toughness from an energy-based homogenization procedure. Another is to define a crack growth-dependent equivalent toughness that involves as the fracture samples different layers. Those ideas are useful, but the figure on the right shows an important difficulty. The error in homogenized description can oscillate strongly at early and intermediate time before gradually decaying. So an effective toughness is not only a material label. During the transition propagation, it may depend on where the tip is, what the layers have already been crossed, and how far the global fluid fracture system are relaxed. This motivates us to look the first at the transition process itself, rather than assuming a homogenization from the beginning. Depending on scale, we can imagine at least 4 descriptions: a homogeneous model, a single interface model, an explicit multilayer model, and a homogenized model. All 4 can operate, but not at the same time and not for the same layer thickness. The key question is therefore, for a given injection time and a given layer thickness, which model should be used? I will first now introduce the governing framework we used in this work. We consider a plane string hydraulic fracture propagating through perfectly bounded linear elastic layers. The fluid is incompressible. In the present formulation, we regulate the leak-off and fluid lag. So the essential coupling is among layered elasticity, viscous fluid transport, and fracture tip propagation. The primary on-loss are opening, the fluid pressure, and the fracture mass. In a homogeneous formation, the coupled problem consists of 3 familiar pieces. First, the elastic equilibrium relates the pressure acting on the fracture face to the opening. Second, a lubrication flow relates the pressure gradient to the rate of fluid transport and the evolution of opening. Third, the fracture tip conditions impose the local asymptotic opening required by fracture resistance. Layering does not fundamentally change the lubrication equation. What it changes is the elastic response and the tip conditions. The first modification appears in elastic balance equation. In a layered medium, the interaction between opening at one location and stress at another is no longer described only by homogeneous color. An additional color term accounts for elastic contrast and the presence of interface. At the same time, the in-situ stress becomes spatially varying along the fracture surface. The interface themselves satisfies continuity of displacement and traction. So the layers remains perfectly bound in this model. At the crack tip, the situation is more abrupt. The near tip opening is governed by the property of the layer that currently contains the fracture tip. When tip enters a new layer, the local fracture energy and elastic modulus can change immediately, and therefore the asymptotic opening also changes immediately. The global fracture shape cannot make the same instantaneous jump. This mismatch between the new local tip requirement and the old global opening profiles is a direct source of non-similar behaviors. We consider three major forms of property contrast: fracture energy, in-situ stress, and elastic modulus. They answer the governing equations differently. A fracture energy contrast directly changes the tip creation. An in-situ stress contrast changes the loading applied along the fracture surface. An elastic modulus contrast affects both the tip asymptotics and the non-local elastic interactions. However, from the viewpoint of the evolving fracture field, they can be reduced to physical disturbance mechanisms. A change in local tip asymptote, and a jump and redistribution in the opening gradient associated with surface loading and elasticity. This slide makes that reduction explicit. Fracture energy changes the near tip asymptotic opening. That is primarily a local disturbance. In-situ stress changes the load transmitted along the fracture and therefore produce an opening gradient disturbance and that propagates through the global field. Elastic modulus does both. It modifies the local tip conditions and also changes the elastic color connecting different parts of fractures. We can now state the central mathematical consequence. In a homogeneous formation, the scanned opening and pressure profiles can remain unchanged during the propagation. The fracture length provides the evolving length scale, and the solution is the safe similar. With an interface, there is a second scale, the fixed distance between the injection point, the interface, and the moving tip. As the fracture propagates, the radius becomes those scans changes continuously. Therefore, the scanned profiles must also evolve. In other words, the interface introduces a spatial reference that can not be absorbed into the fraction length. I will now focus on one interface and show how this additional parameter organizes the transient response. Suppose the fracture reach an interface after propagating a distance L sub 0, and then penetrates an additional distance d into the second layer. We define a relative penetration distance and phi equals d over L sub 0. The total length is L sub 0 plus d, and the spatial coordinate is normalized by the current fraction length. The important change is that the dimensionless opening and pressure no longer function of the similarity coordinate alone. They now also depend on the implicitly on phi. So phi is an interface evolution coordinate. Immediately after crossing, phi is small, and the tip moves farther away, phi grows. Because the scanned profile depends on this evolving parameter, the solution is intrinsically non-self-similar during the transition. After introduce this scaling, the dimensionless equations contains an additional evolution term involving the rate of change of phi. I delete the classical viscous contribution by M, which is related to background dimensionless toughness. In a toughness-dominated homogeneous fracture, M is small. But after an interface crossing, the effective viscous term contains by the product of M and the rate of interface relation evolution. This is an important result. A small background viscous coefficient does not generate a negligible viscous displacement if the interface relative evolution is sufficiently rapid. So the interface can temporarily amplify viscous effects in a system that would otherwise be classified as toughness-dominated. The physical sequence is shown here. Before crossing, the fracture is in a toughness-dominated region. Both classical viscous term and interface-induced convection are small. Immediately after the crack, the tip enters the new layer. However, the required opening changes abruptly. Fluid must be redistributed. The rate of evolution of phi becomes large, and the interface-induced viscous contribution can become an odd one. Far from the interface, the redistribution gradually relaxes. The rate of interface relative evolution decreases, and the fracture approaches the homogeneous toughness-dominated solution of the new layer. Let us begin with the simple case, a contrast in fracture energy. The curves show how the fracture length responds when tip curls from one layer to another with different fracture energy. The low panels shows the involving of fracture shapes. If the new layer has low fracture energy, the fracture accelerates. If it has a high fracture energy, the fracture slows. But in other cases, the response is not an instantaneous jump from one homogeneous solution to another. Instead, the fracture passes through a continuous non-shift-familiar transition. The important observation is that the transition has a finite duration and a finite penetration distance. Once this distance is identified, we can ask whether the next interface is encountered before or after the current disturbance has relaxed. For fracture energy case, mass conversation provides a useful estimate of the transition distance. At the instant of crossing, the fracture contains an initial fluid volume. After crossing, continued injection and Q sub-zero product T, the evolving fracture volume must equal the sum of those contributions. If we assume the interface-induced convection relaxes magnetically towards the new layer homogeneous solution, we can draw an upper bound for the relative penetration distance. The expression shown here depends on three quantities: the original interface distance, the fracture energy ratio, and the normalized elapsed time. The exact prefactor is less important than the structure. The transition distance grows with the scale of the incoming fracture and changes systematically with the property contrast and elapsed time. This gives us a candidate spatial measure of the interface influence. We then compared this scanning with numerical solutions. The symbols are numerical transition distance, and the solid curves are theoretical predictions. A single normalized creation with fitted transition value, shown here, collapses the case with different fracture energy ratios. More importantly, the same creation also collapses case in which the interface is reached at a different time or equivalently at a different initial fracture length. So the transition is not controlled independently by contrast and arrival time. Those effects enters through a common scan measure. This is the first evidence that spatial extent of an interface disturbance can summarized by a critical penetration distance, which I will denote by delta. For an in-situ stress contrast, an additional parameter is required because the disturbance has both a position and an amplitude. We again use phi equals d over L sub 0 to describe the relative tip interface position. We then introduce a dimensionless stress contrast magnitude gamma, which scans the stress jump by the fracture mechanics qualities of the incoming layer. The co-analytical relation expression the derivation of fracture length from the homogeneous reference is in terms of phi and gamma. This interpretation is straightforward. Phi tells us where we are in the transition, while gamma tells us how strong the disturb is. The sign of the stress contrast determines the direction of response. If the stress ahead of the tip is low, the effective resistance decreases and the fracture accelerates. If the stress is high, the propagation rate is reduced. The evolving opening profiles show that effect is not only a change in tip speed, the interface also changes the storage volume in the correct tip, and that allows the storage is coupled to fluid redistribution. When the numerical results are plotted against the phi, the different stages of transition become more systematic. For the relatively small gamma, the transition occurs approximately the same value of phi. At the larger stress contrast, enhanced fluid redistribution and viscous dissipation shift the transition location. The numerical result also approach the analytical predictions as the tip moves farther away from the interface. So for the stress contrast, the same conceptual separation holds. Phi is the spatial evolution coordinate, and gamma determines the disturbance amplitude and modifies the quantitative transition threshold. Elastic modulus contrast is more complex because it activates both interface mechanism simulators. The numerical results show corresponding changes in both propagation history and fracture shape. The comparison across all three types of contrast leads to a common critical penetration distance delta. Although the fracture energy, stress, and modulus enters through different governing terms, the spatial range over which an interface significantly affects propagation can be characterized using this same concept. From data, we can define a characteristic time like this, where the G is taken as the maximum relevant fracture energy, and E as the minimum effective modulus. The purpose of this expression is not to claim that every contrast produces identical amplitudes. It says that their reaction range be organized by a common penetration scheme. This is a bridge from a single interface to multilayer propagation. I will now use this single interface influence distance to ask what happens when the next interface arrives before the current disturbance has fully relaxed. In a multilayer system, every interface cross generates a new local disturbance. The tip condition changes the abruptly and the crossing. The globe opening and pressure field then begin to adjust through fluid distribution. But before the process is complete, the fracture will reach the next interface, which the interrupt and restart the transition. Therefore, the multilayer propagation can be viewed as a sequence of interacting single interface transition. This interpretation is useful because it turns a complicated multilayer problem into a transition of computation between two distances. The distance required for one disturbance to relax, and the distance avoidable before the next interface is reached. Let the layer thickness be d, and let the single interface influence distance be delta. Three reservoirs follows naturally. If d is much larger than delta, the disturbance relax before the next crossing, and each interface can be treated approximately independently. If d is comparable to delta, the next interface is reached while the previous disturbance is still relaxing. We then have a coupled transition. If d is much smaller than delta, successive disturbs overlaps continuously, and the fracture experiences a genuinely multi-layer interaction. So layer thickness is not just a geometric input. It limits the spatial distance available for the fracture to forget the previous interface. The spatial argument can be converted to a time scale. In the single interface problem, delta defines the reduction distance. In a periodic multilayer system, the relevant limited distance is d, because the next interface arrives after one layer thickness. Replacing delta by d gives a new characteristic multilayer time like this. This is the time required for evolving the fracture influence scale to become comparable to the layer spacing. We can now define the central dimension parameter of the talk K. The K is determined by the small t over the large T, and this is the K temporal-spatial scaling law. It involves the elastic modulus, ejection rate, time, layer thickness, and fracture energy. Increasing ejection time increase K, and decrease layer thickness also increase K. Those two apparently different operations therefore move the fracture in the same direction through the region map. That is why K is useful. It converts the time and spatial layer into one evolution coordinate. The physical interpretation of K is perhaps even more important than the formula. When K is small, the evolving fracture influence length is much smaller than layer space. The fracture mainly sense its current local environment and interface are effectively unsolved. At immediate K, a single interface can dominate the transient response. And large K, the influence length spans multiple layers and successive interface disturbs interact. At a very large K, the individual layer scale oscillations become too far relative to macroscope propagation scale. The response across a homogenized description. So K describes the propagation stage. It does not, but itself describe how strong a particular interface contrast is. This leads directly to four modeling regimes introduced at the beginning. At a small K, a homogeneous description may be sufficient because heterogeneity has not yet been dynamically resolved. At K increase, the single interface model becomes appropriate when one crossing dominates the response. At a larger K, multiple interface disturbs interact and an elastic multi-layer description is needed. Finally, at a very large K, the layer scale oscillations become macroscopically unresolved and a homogenized model becomes appropriate again. Let us test the scaling with periodic fracture energy contrast. In dimensional time, different layer thickness produce very different propagation history. This layer leads to frequent switch between faster and slow state as the tip rapidly encounters low and high fracture energy layers. Thick layers produce few more widely separated transitions. If we look at dimensional time, those cases appear to fundamentally different. We can see on the left, the oscillation occurs at different dimensional time for different layer thickness. But on the right, after plotting the same response against K, the stage transition align much more clearly. We can identify the early homogeneous stage, a region where the individual crossing are important, a multi-layer interaction region, and finally a decay toward homogenization. The important result is that the boundary between propagation stages are organized by the same dimension is evolution coordinate. We can also test the problem using the periodic in-situ stress constant contrast and the periodic monastic modulus. Their results are same. At this point, an important qualification is needed. The property contrast is still matters. Stronger fracture energy stress or module contrast produce larger disturbance amplitudes. They can also shift the quantitative values of K at which adjacent interface disturbs begin to interact. So regional boundaries are not universal contrast independent of material contrast. What is more robust is the direction of evolution. As K increases, the system proceeds from weakly resolved heterogeneity through interface-dominated to multi-layer behavior towards homogenization. Thus, K is the common evolution coordinate, while the property contrast controls the amplitude and the precise threshold values. We can now put the classical homogeneous parameters and the new layered parameter together. The dimensionless toughness sets the background hydraulic fracture region. At a larger kappa, the fracture is toughness dominated and is strongly sensitive to changes in interface resistance. At the intermediate kappa, the toughness and viscosity dissipation both matter. And the small kappa, the fracture is viscosity dominated and the interface sensitivity becomes weaker. By contrast, K tells us where the fracture is in the temporal-spatial evolution through the layered system. So those two parameters are different roles. Kappa controls the strength of interface response through the background propagation region. K identifies the stage from homogeneous single interface, multi-layer, or homogenized model. Let me finish the implication from homogenized modeling and then summarize the main conclusions. Our implication is that homogenized hydraulic fracture models need to contain two conceptually different components. The first is the effective elastic response of the layered solid. Classical homogenization of elastic layers proceeds transverse isotropy, and that part can be described using established effective elastic property. The second component is the effective fracture response. Repeated interface crossing creates a pulse-dependent, direction-dependent resistance. Let me summarize the main conclusions. First, interface breaks the classical similarity. The tip conditions can change immediately at a crossing, while the global opening and the pressure field adjust progressively through fluid redistribution. Second, for a single interface, the relative penetration coordinate provide a natural measure of transient evolution. Although fracture energy, stress, and modulus contrast act through different mechanisms, their spatial range of influence can be characterized using a common critical penetration distance. Third, for the particle multilayer, replacing that penetration distance by the layer thickness lead to a characteristic time and to the dimensionless time parameter k. This parameter combines injection time and layer thickness and organizes the transition among four modeling regimes: homogeneous, single interface, multilayer, and homogenized. Finally, the classical dimensionless toughness and the new temporal-spatial parameter plays complementary roles. Kappa controls the background propagation region and interface sensitivity, while the K identified the evolution stage. Thank you very much for your attention. This is all of my presentation, and I would very happy to discuss the problem. Of course, you are all very welcome to visit us at the university. Thank you. I'm look forward your question.
Thank you, Hao. That was really an insightful talk, and we greatly appreciate it. I don't have any questions, so I'll just ask, what are your future plans? What do you plan to do next?
My future plan, you can see in my current work, I just found a dimensionless parameters that measure the evolution of a fracture from homogeneous single interface and multi-layers and finally a homogenized model. But this is not a universal law for the hydraulic fracture modeling. I want to know what is the contrast and what is the effective fracture toughness along this evolution process. This is not solved in this work. And another future plan is for a more realistic model, like a three-dimensional model. This work is based on the classical KGD model. This is an idealized model, but for the real three-dimensional model, this conclusion it can be used for the real world. I'm not sure. So I think I have do some work to make this work for a real three-dimensional model. This is my my plan to the future research work.
Okay. And we do have a couple of questions that have just popped up, and one is from Tao, and Tao is curious, what will happen if fluid lag is considered? Will it change any conclusions?
I'm sorry, I have some problem for my internet. Okay.
Okay, but we can hear you.
Okay.
Yeah. So Tao's question was, he's interested, what will happen? What do you think will happen if fluid lag is considered, and will it change any of your conclusions?
Uh, can you say it again? I don't get your words.
Okay. Can you see the chat by any chance? What about fluid lag?
Fluid lag. Uh, um, I I I I considered this problem before, and I want to solve the fluid lag. Maybe it may be a very important role on this model because we can find if the viscous dissipation is reduced by interface is because it always always combined with the fracture. So if there exists a fluid lag, the fracture may be propagation far away from the uh, fluid fluid front. So the interface disturbs on fracture propagation. It will not be influence on the fluid redistribution in the fracture gap. So this is an important problem, and but it is I have some problem to solve this problem concerning the fluid lag and the layered heterogeneity and the fracture propagation. I have some coding problem in this problem, so I think this is an important problem, but I have not solved this problem now. Maybe I this is also a problem I want to solve in the future research work.
Yeah. Okay. Very good. Future consideration.
Yeah,
And,
and this is a very important problem. I
yeah.
think.
And Tao agrees. He says it will be very interesting.
Yeah.
One observation from James is that he found this very interesting, but it would be very nice if the future work could incorporate some field observations and calibrations, if that's at all possible. And that may or may not be possible, but that's a recommendation.
Okay. Thank you.
Yeah, yeah. Laura, yes, this will be recorded. And it'll
Have a comment, John, if you don't mind.
oh,
Yeah.
by all means, Igor.
Thank you. Yeah, well, I'll just would like to second everyone and thanks Hal for the seminar. I just have a comment is like, I think kind of one of the important things again it wasn't said kind of directly, but what Hal is doing is not something that is a lot of people are working on, right? So it's more of like fundamental hydraulic fracture mechanics from like solid mechanics point of view, right? And so unfortunately, actually, in the US, there's not a lot of kind of supply of young researchers in this area, right? Because there is no funding in this area, and so I think for the hydraulic fracturing community, it's very important to have representation of presentations from people like Haobik, because again, basically we do not have a lot of research in this area anymore in the US, unfortunately. So I think this is something to keep in mind. And the second thing is also, just more like a question to how, because I visited him, last year at USTC, and so there's also a lot of other directions that he's working on, specifically related to computations. So I don't know how if you can comment a little bit more about directions that you're working on with regard to numerical methods, right? So I know you're doing like phase field, XFEM, and displacement discontinuity for fraction modeling, but is there anything else you are working on in this regard?
Okay. Thank you, Igor. We have a very young research group in USTC, and the hydraulic fracturing in China becomes an important thing in China. So we have many students focus on the modeling of hydraulic fracture, and we have about 10 students in my research group, and we focus on different computational methods like the phase field model and the XFEM extended finite element method. And also we do some deep learning. And this is three core directions of our research groups. And for XFEM, we want to use this method to combine the theoretical corrective solutions with numerical method to resolve the large-scale fracture predictions. And for phase field method, we know it can capture very complex fracture geometry during we use injection by fluids like water or CO2 into the receiver. It may be generate more complex fracture geometries. And phase field also provide very useful and powerful tool for the multi-physics coupling problems. And for the deep learning method, we use this method to reconstruction the rock, the core of the rock under the conventional reservoirs. So we have different numerical method, but we also most of the method we want to find its application in the petroleum engineering to prove its application on the hydraulic fracturing or the explosion like this.
All right. Thank you.
Thank you, Igor.
Well, How, I'd like to thank you again. This was fantastic. You generated a lot of interest, and I'm with Yegor. It's nice to see this fundamental research going on. So congratulations and thank you again.
Thank you, John. Thank you, everyone, for your attention.
Yeah. Thanks, everyone. We'll see you in 2 weeks.